Welcome to the lecture on Engineering Economics Evaluations. As you view this presentation, please compile any questions or comments you may have and email them to me. I will try to address them as soon as possible. So to begin, the reason we are exploring this subject is because, as engineers, we are generally tasked with developing an alternatives analysis for a client. This allows the client to see various design approaches for a particular outcome. Not only do we try to highlight the differences in the design approach, but we illustrate the differences in costs, benefits, and life cycles. Each alternative is unique with regard to these elements. For example, we could show two alternatives for the design of a dam. Alternative 1 is a large-scale concrete dam, a robust structure that is very expensive in terms of materials and labor-intensive, but will ultimately save the client money in maintenance costs and will also have a much longer design life. Alternative 2 would be, say, an earthen dam, which is relatively cheaper to construct since it doesn't require any skilled labor and uses inexpensive materials. However, the earthen dam will need much more maintenance to repair parts of the dam that erode away, among other things. Also, the design life is going to be much shorter. So, what we will do in this lecture is use the equations we learned in the previous Basic Engineering Economics lecture to help us explore the methods used to illustrate these comparisons. The first method is the present worth net benefit, or PWNB. Now what this method does, it helps us determine which project has the greatest net benefit relative to a lump sum in today's dollars. The second method is the annual net benefit, or annual cash flow. It is essentially the same method as the PWNB, but in this case, instead of a lump sum in today's dollars, we are comparing the benefits in terms of an annual revenue stream. In other words, we're trying to determine which alternative gives us a larger annual revenue. The next method is the payback period. The payback period simply illustrates which alternative gives us a return on our investment in the shortest amount of time. Next is rate of return, which we signify with our I star. Rate of return determines basically at what interest rate our costs and our benefits equal out. And finally, the benefit-cost ratio allows us to qualify if an alternative has a positive net benefit. So let's start with present worth net benefit. In this method, we look at all of the benefits and costs associated with an alternative, like the one shown here in this cash flow diagram. We then convert each of the costs and benefits into a present worth. The costs will be negative and the benefits will be positive. So the net present worth determines if it is an overall benefit or a cost in today's dollars. So let's look at an example. In this problem, we are looking at two alternatives. Alternative A has a capital cost of $5,000 and a projected net revenue in equal annual payments of $2,000 for 5 years. It also has an operational and maintenance cost of $500 per year. Alternative B has a capital cost of $9,000 and a projected net revenue in equal annual payments of $3,250 for 5 years. It also has an operational and maintenance cost of $250 per year. So at 5% interest, which alternative has a greater benefit in today's dollars? The first thing we do is develop a cash flow diagram. So for alternative A, we show our capital cost of $5,000 in red pointing down at year 0. We also showed the $2,000 annual revenue at the ends of years 2, 3, 4, and 5 in green pointing up. Conversely, we show the operational and maintenance or O&M costs of $500 in red at the end of years 1, 2, 3, 4, and 5. For alternative B, we show our $9,000 capital investment in red pointing down at year 0 and the $3,250 annual revenue at the ends of years 1, 2, 3, 4, and 5, pointing up and in green. We also show the $250 O&M cost in red at the end of each year, pointing downward. Another helpful tool is to break out our costs and benefits in a table for each alternative. So as the problems become more complex with added revenue streams and additional costs, we are able to look at the net revenue for our calculations. So here we see that alternative A has a net revenue of $1,500 for the ends of years 1, 2, 3, 4, and 5. Alternative B has a net revenue of $3,000 at the ends of years 1, 2, 3, 4, and 5. We get there by subtracting the O&M costs from the annual revenue stream. So now our equations are much simpler. We sum together all of our costs and benefits in terms of present worth. So for alternative A, we don't need to convert the $5,000 since it's already in today's dollars, but we do need to convert our net revenue of $1,500 into present worth using our uniform series present worth equation that you will find on the handout given out in the last lecture. So we determine that alternative A has a total present worth net benefit of $1,494.22. For alternative B, we do the same thing. We leave the $9,000 since it's in terms of present worth, and we convert the $3,000 net revenue. We find that the alternative B has a present worth net benefit of $3,988.43. So, in conclusion, alternative B has a higher overall net benefit in terms of a lump sum in today's dollars. So if you wanted to analyze a present worth net benefit using Excel, we would use the NPV function. And the way we input that is to first type the function NPV into a cell. Then select the cell containing the interest rate. So in this example, it would be cell F2. We then hit comma, and then select the series of values representing the net revenue at the end of each year. What this gives us is the present worth of the annual series. To get the present worth net benefit, you have to take it a step further and add it to the capital cost. B3 for alternative A and D3 for alternative B. So you see that we end up with the same values that we calculated using the equations. Annual cash flow, or annual net benefit, is based on the same principle as present worth net benefit, except here we are converting all of the costs and all of the benefits to an annual series. So whichever alternative has the greater net revenue at the end of each year of its project life is the project that is more beneficial overall. So for the annual net benefit example, we are going to use the same example we used in the present worth net benefit example to illustrate the similarities between the two methods. The cash flow diagrams are the same as the cash flow diagrams we drew in the present worth net benefit example problem. The cost benefit table is the same as the present worth net benefit example. Now, the difference here is that we convert the costs and benefits into annual series. So for alternative A, we take the $5,000 capital cost and convert it into an annual series using the capital recovery equation. We keep the $1,500 net benefit as is, since it is already in terms of an annual series. We end up with an annual net benefit of $345.13. For alternative B, we convert the $9,000 capital cost to an annual series and add it to the $3,000 net revenue and end up with an equivalent annual net benefit of $921.23. So just as in the present worth net benefit example, alternative B is the more beneficial alternative. For an Excel solution, we can use the PMT function. With this function, we type in PMT into the cell, and we first select the cell containing the interest rate, in this case, cell F2. Then, we select the cells containing the number of years in this series. In this case, we select the cell containing 5, so cell A8. This is used for both alternatives. Next, we select the cell containing the capital cost that we are converting into an equivalent annual series. For alternative A, we're selecting B3, and for alternative B, we are selecting D3. Now, for some reason, the PMT function automatically converts it to a negative. So make sure when you input the capital cost into Excel, you input it as a positive. We then take the PMT function a step further and add it to the cell containing a value representing the annual series. So for alternative A, we're using cell C8, which has a value of $1,500. For alternative B, we use cell E8, which has a value of $3,000. And as you can see, we end up with the same answers that the equations gave us. Now, in most cases, different alternatives will have different project lives. You can't simply do a present worth net benefit or annual net benefit on them because it would not be an accurate comparison. If that were the case, the outcome would be skewed to the alternative with the longer project life. So what we do instead is find the least common multiple of the project lives and then repeat the cash flow periods so the alternatives have an equal project life. For example, if we are comparing alternative C that has a 15-year project life and alternative D that has a 10-year project life, we would analyze them both with 30-year project lives, where alternative C will have 2 project life cycles, and alternative D will have 3 project life cycles. We do this by repeating fixed costs such as capital costs and salvage price at the same year interval. For example, we have two alternatives. Alternative E has a capital cost of $4,000 and a projected net revenue and equal annual payments of $500 for 4 years. At the end of the project, the engineer projects selling the equipment for a salvage price of $600. For alternative F, we have a capital cost of $6,000 and a projected net revenue and equal annual payments of $750 for 3 years. At the end of the project, the engineer projects selling the equipment for a salvage price of $800. Using an interest rate of 6%, we need to determine the present worth net benefit of each alternative. First, we have to determine the equivalent length of the project life at which both alternatives can be analyzed. Since the least common multiple of 4 years and 3 years is 12 years, each alternative will be analyzed with a 12-year project life. So alternative E will have 3 life cycles, while alternative F will have 4 life cycles. So let's look at alternative E first. We set up a cash flow diagram with its normal 4-year project life. We have our $4,000 capital cost, our $5,000 annual revenue, and a salvage price of $600 at the end of the project. So we repeat the entire cash flow diagram once and then twice until we have 3 life cycles totaling 12 years. So we repeat the capital costs of $4,000 at year 4 and at year 8. We also repeat the salvage price at years 8 and 12. We also have a total of 12 annual revenues of $500. Now we look at alternative F. We create the cash flow diagram with the $6,000 capital cost, $750 annual revenue at years 1, 2, and 3, and an $800 salvage price at the end of the project, year 3. Then we repeat it once, twice, 3 times until we have 4 life cycles with a total project life of 12 years. We repeat the $6,000 capital cost at years 3, 6, and 9. We also repeat the salvage price at years 6, 9, and 12. We have 12 annual revenues of $750. So now that we have made the alternatives equal in project life, we can now look into condensing the cash flow to make it easier to calculate. Putting it into tabular format helps to illustrate the repeating life cycles and how that affects the net revenue at the end of each year. More specifically, years that are key for repeating, such as for alternative E, year 4 and year 8. For an Excel type solution, creating a table such as this would be beneficial. But in order to calculate using equations, it is easier to simplify the different costs and benefits to make the equation less complex. So, in order to do a present worth net benefit, we would need to convert all of the $500 revenues into a present worth and treat each $4,000 capital cost and $600 salvage price as individual future worths to be converted to present worth. We can simplify this by combining the salvage price and the capital costs at years 4 and 8 to get a net of $3,400. We don't include the $500 at year 4 and 8 in that net because we want to keep it as a continuous 12-year series. Now we only have to convert the annual series, $3,400 at years 4 and 8, and $600 at year 12 to present worth. Same thing with alternative F. We'll combine the $800 salvage price and $600 capital costs at years 3, 6, and 9 to get a net of $5,200. Now we just have to convert the $750 revenue stream, $5,200 future worths at 3, 6, and 9 years, and the $800 salvage price future worth at year 12. So here we have the equations for each alternative. We convert the annual series to a present worth using the uniform series present worth equation. We convert the future worths to present worth using the single payment present worth equation. We conclude that while neither analysis show a benefit, alternative E has the least costs and thus more beneficial relative to alternative F. So our next method is called payback period. This helps us to determine at what year in the project's life do we receive a return on our investment. In other words, at what year is our net revenue equal to our startup costs? It is important to understand that this method is not to be used to determine which project has a higher benefit. It is only to determine when a project has become profitable. There are two types. The first is undiscounted payback period, which does not include interest rate, so it is much simpler. The other is the discounted payback period, which includes interest rate, and is conducted by doing an incremental present worth analysis. Let's look at an undiscounted payback period example. We have 3 alternatives with various revenue streams. Alternative A has a capital cost or investment of $1,000. Now, as we add up the revenues at the end of each year, we find that by the end of year 3, we have made our $1,000 back because we have added up the $500, $300, and $200 revenues. Same thing for alternative B. We start off $1,000 in the hole. At the end of year 1, we are at negative $800 due to the $200 revenue. By the end of year 2, we are at negative $500 with the $300 revenue. So after making $500 at the end of year 3, we have a net cash flow of $0. For alternative C, we start off with an investment of $700, but lose an additional $300 at the end of year 1. By the end of year 2, a revenue of $500 has brought us up to negative $500. And by the end of year 3, we are at $0. So, each of these alternatives have the same payback period of 3 years. But if we do an undiscounted present worth analysis, we find that each alternative is much different in its present worth, with alternative B being much profitable than alternative C, regardless of their equal payback periods. For the discounted example, let's take a look at just alternative A. So now we have an interest rate of 15%. The method is the same as the undiscounted. We still incrementally add up the revenues at the end of each year, but in this case, we use the single payment present worth equation to take each revenue amount, treat it as a future worth, and convert it to present worth. So, we start off $1,000 in the hole. We make $500 at the end of year 1, but we discount it at 15% and convert it to a value of $434.78 in today's dollars. This brings us to a total of negative $565.22. We do the same with year 2's $300 revenue. We discount it, add it to the negative $565.22, and get negative $338.33 net revenue at the end of year 2. We do this incrementally until we are in the net positive amount. This doesn't happen until the end of year 5. So you see how interest affects the payback period and the return on one's investment. The next method is rate of return. Now, this method allows us to determine the interest rate we would need so that our net benefits would equal 0. In other words, our benefits equal our costs when our interest rate is our rate of return. The way we do this is to do a present worth net benefit or annual net benefit analysis and set the equation equal to 0, except we leave the interest rate I as a variable. We then solve for I. This interest rate we solve for is our rate of return. For the rate of return example, let's look at this particular cash flow. So the first thing we do is we develop our cash flow diagram. So here we can clearly see our costs and our benefits. For this example, we are going to convert the values in terms of present worth. There are many different ways to do this, so I will show you 2 options. Now, option 1 takes each value as a future worth and uses the single payment present worth equation. So we have our $1,000 capital cost, and we convert the future worth of $800 to present worth at year 1. We convert the $500 at year 2, $500 at year 3, $500 at year 4 individually as future worths. And finally, we convert the $1,200 at year 5 to present worth. For option 2, we again take the $1,000 capital cost, no need to convert it, And we also do the $800 future worth at year 1. But for this option, we create a $500 annual series from years 2 through 5. That's why you see the number 4 here in the number of years part of the notation, because it is an annual series through 4 years, years 2, 3, 4, and 5. But like I said in the previous class, when we do a uniform series present worth, it will calculate the series' present worth just to the year before it. So just by doing this part of the equation, we're calculating the present worth at year 1. So we have to take it a step further and do this part of the equation, which converts that value as a future worth from year 1 to a present worth. It is also important to know that the $1,200 at year 5 has $500 subtracted from it. So we're left with a $700 future worth at year 5 that we need to convert. In either case, we take our costs and our benefits, our costs being negative and our benefits being positive, and set them equal to 0 with I as our variable. Understand that these are just notations. Each notation represents an equation. I decided to use the notations instead of the equation to make sure that the slide did not get jumbled. Even not seeing the equations, you can imagine that the mathematical process for solving for I would be quite complicated. This is why I suggest using Excel for rate of return problems. Essentially, you would create all of your PWNB or AMB equations and iteratively change the value of the interest rate until you get a present worth net benefit or annual net benefit of 0. In this case, we solved for I and got a rate of return of 12.8%. Lastly, we have the benefit-cost ratio. This method simply gives you a quick glance at whether your alternative is beneficial or not. You can then use this qualifier to compare to other alternatives. So you simply convert your benefits and your costs to the equivalent time, whether it be present worth or an annual net benefit, and you divide the benefits by the costs. If the value is greater than 1, that means the project is profitable. The benefits are greater than the costs. If the benefit-cost ratio is less than 1, then your costs are greater than your benefits, which is generally bad. Let's look at this example. We have two alternatives, alternative G and alternative H, each with a unique revenue stream. Now, using an interest rate of 12%, we'll convert these values to present worth, separate the costs from the benefits, and find the ratio. So, for alternative G, we treat the $500 and $300 benefits as future worths at years 1 and 2, respectively. We then convert the revenue series of $200 to present worth, but need to take the extra step to bring it to year 0. The costs of this alternative are simply the $1,000 initial cost. For alternative H, we convert the two $500 benefits from a future worth to a present worth. Our costs are the $1,000 initial cost and the $300 loss in year one, which we convert to a present worth. Now, we simply take a ratio of our benefits to our costs. And we find that for alternative G, we have a benefit cost ratio greater than 1, meaning the benefits outweigh the costs, while alternative H has a benefit cost ratio less than 1, meaning the costs are greater than the benefits. So in this case, you would select alternative G. So that concludes this week's lecture of Engineering Economics Evaluation. Please continue to work on the after problems for this chapter and the before problems for the upcoming scheduling chapter before next week's class. If you have any questions with this lecture or the homeworks, please feel free to contact me. Also, please check your emails this week as to whether or not we will be meeting in class or if I will be sending another video lecture. Thank you for watching and listening, and have a great rest of the week.